This is the second lecture of chapter 12, which deals with elimination reactions of organic chemistry. You will recall that the approach in learning organic chemistry is to know the different types of reactions. We've covered quite a few before: acid-base reactions, oxidation, reduction, etc. Now we're looking at elimination reaction. For today's presentation, we will do a quick review of the E2 reaction mechanism, which was covered in the previous lecture. And then we will go into looking at another mechanism, the E1 mechanism, for the same elimination reaction. Then we look at some reactions involving haloalkanes and alcohols, and then we will conclude by applying these reactions to synthesis. So let us start. A quick review. You will recall that elimination reactions really involve the removal of atoms or groups of atoms from adjacent carbons of a molecule. And the removal results in an unsaturated molecule, typically an alkene. Here are two examples which we covered earlier. This is the elimination of HCl, H and Cl. Notice it's across adjacent atoms, 1 and 2 atoms. In the presence of a base and heat, we get an alkene, a double bond, and of course some inorganic products. It's possible to eliminate water, H2O, and we have our alkene right here on saturation. What we'll emphasize today, though, is what happens when we mix the reactants and eventually get the product. What goes on to transform the reactants into products? We'll describe that description as the mechanism. Remember, a mechanism is a step-by-step description of a reaction or how that reaction proceeds from reactants to products. So that's the mechanism. And you'll see why it is so important to know the mechanism of reactions, because it can be used to explain various observations. So let us look at what we did earlier. The first mechanism to explain the elimination reaction was the E2 mechanism. And remember, that's E2, there's an E elimination and a 2 here. What does that 2 mean? That 2 means that there are 2 reactant molecules in a single step to form the product. Reactant molecule 1 is the base, and reactant molecule 2 is the organic molecule with the leaving group, typically a halide. So these 2 molecules in a single step goes to form the alkene. Since it's a single step, there is one transition state for that step. Notice the transition state here is shown by dotted lines. Remember, dotted lines here mean that they are partial bonds. Remember, transition state is a description of the reactants going to products. So in that transition, we have partial bonds being formed and partial bonds indicating bonds being broken. One aspect I should remind you of, it's a transarrangement. So we need the hydrogen that's being taken off as a proton. Remember, a proton here is hydrogen without its electrons. So these electrons here swing in to form the double bond, and this leaving group here leaves with its electrons to form the leaving group. So that is the elimination reaction, and specifically the E2 mechanism, where E2 refers to two reactant molecules in a single step to form the product. Let us go into the E1 mechanism. So here's another explanation for the same reaction. So we're just looking at another explanation or mechanism for the same reaction. Let's see how that would work. So here we have just the organic molecule with the leaving group. If the leaving group is exceptionally good, a very good leaving group, you can imagine it leaving with its bonding electrons. And that's why we have this arrow here showing that this bond is broken and the electrons go with the leaving group. That's why it's an X minus. What's left behind is a carbocation because those electrons are gone. A carbocation, as you will recall, is a cation which has a positive charge on carbon. So this is a carbocation. It's an intermediate. It's not stable. So in another step, here comes the base. The base comes in, abstracts that hydrogen as a proton, leaving these electrons to swing in to form this double bond here, and that's the product. So why is it called an E1? It's called an E1 because in the first step, which is the most difficult step as you can imagine, because we're going from a neutral molecule here to an intermediate, that's called the slow step or the rate determining step. That's the most important step of the reaction, and that is the step in the reaction mechanism that determines the overall rate of the reaction. So in the most important step, in the RDS, there's only one molecule, and that's why it's called an E1. In the fast step, the base comes in, the second molecule comes in to abstract this as a hydrogen, a proton, but that's in the fast step. That does not determine the overall rate of the reaction. That's why it's referred to here as the fast step. So this is the E1 mechanism. So in the first step, or the rate determining step, one reactant molecule, the reactant molecule, the organic molecule that has the leaving group leaves with its bonding electrons to form a carbocation. And in the fast step, the base abstracts a hydrogen adjacent to the carbocation. Notice it's adjacent to the carbocation. So you can imagine it's possible to form a double bond over here also. But we'll discuss that in a second. As you know, in organic chemistry, we can describe a concept or a mechanism by using a diagram. Here, this is called the energy profile or the reaction profile, where energy is in this direction here, and of course we have here the reaction coordinate, which means that we have reactant here and product over here. So we're trying to monitor the progress of the reaction here, and we're trying to see how the energy of the intermediates changes. So we start off here with the reactant, the organic molecule with the leaving group. As we said, if it's a good leaving group, the leaving group leaves to form a carbocation right here. So this represents the first step of the reaction right here. In the second step, the carbocation reacts with the base and goes to form the product. So it's a two-step reaction, but the most important step is the first step. Why? You can see here again the energy of activation for this step here is pretty large. As you will recall from Gen Chem, if the energy of activation is large, the reaction is slow. So that's why it's called the slow step. The energy of activation here for the second step, as you can see here, is small. So therefore, it's a fast reaction. That's again why it's called the fast step. So most important here, this represents the E1 mechanism, the reaction profile, two-step reaction, showing an intermediate where the activation barrier to form the intermediate is much higher than the activation barrier from the carbocation to form the elimination products. Let us look at a real molecule here and see how we can apply the mechanism. So here is a real molecule. As we said, if it's going by E1, the leaving group leaves. As you will recall, Br is a good leaving group. So look at your periodic table and you'll see that Br is to the right and of the periodic table, and it's pretty large. So therefore it is electronegative and also large and can accommodate 2 electrons. So it leaves with its bonding electrons. That's why we have this arrow right here. So again, in writing your mechanism, that's why we say use arrows to indicate electron movement. So this arrow is indicating that these 2 electrons go on to bromine to form bromine negative. What's left behind is a carbocation intermediate. That's the rate determining step, RDS, the slow step for that reaction. This is not the product, it's an intermediate. In the second step, the base pulls off a proton, a hydrogen as a proton. In this case, we do not, the solvent, which is ethanol, is a strong enough base. It's a weak base, but strong enough to pull off this hydrogen as a proton, and these electrons here swing in to form the double bond. And that's in the fast step. Notice that the major product that's observed, if you did this experiment in the lab, is this as the major alkene product. You may be wondering, why isn't this, the double bond formed over here, the major product? Let's see why. And that again shows the importance of understanding the mechanism. Why isn't the other product the major product? Let's see why. If we have this intermediate here, notice the carbocation is right here. This carbon has that positive charge. So the double bond can be formed either here, here, that would be the same, or here. The ethanol, as a solvent, can pull off this hydrogen to form the double bond here, as shown. It can pull off this hydrogen here, or one of these hydrogens here, to form the double bond here, as shown. So there are 2 possible products. This product, however, is the major product because it is the more highly substituted alkene. What do we mean by more highly substituted alkene? Here are the carbons of the double bond, and on those carbons, on those 2 carbons, are 1, 2, and 3 alkyl group. So we say it is tri-substituted double bond. You will recall the stability of alkenes depend on the number of groups surrounding the carbon-carbon double bond. The more substituted, the more stable will be that alkene. So this is a tri-substituted double bond, also made reference to in previous chapters as the Zaitsev product. If we should pull off this hydrogen or one of these hydrogens here to form the double bond here, here are the 2 carbons of the double bond. It has 1 and 2 alkyl groups. Notice these are hydrogens. so they're not considered alkyl groups. So we have two alkyl groups, so therefore it is a di-substituted double bond, and therefore less stable than a tri-substituted alkene. We make reference to this as the Hoffman product, as we did show it in last lecture. So that's why this is the major product as shown before for that reaction, and this is the minor product. So when you're asked to predict the major product of a reaction, you need to know the mechanism. If it's an E1 mechanism, the more substituted product will be the major product. Okay, let us look here at a substitution looking at a slightly different molecule. So here we have a carbon and 3 methyl groups and a good leaving group, bromine. So there's only one possible product here, forming the double bond between this carbon and one of these carbons. What I want to point out here is that if we went with just alcohol, just the solvent, the alkene that's produced is an 80% yield. But if we did the same reaction and introduced here a strong base, such as potassium ethoxide, the percentage of the same alkene jumps up to 93%. You will recall from the previous lecture that the E2 mechanism, let me say that again. You will recall from the E2 mechanism that the base plays an important role in forming the product. That's why it's called an E2, because the base and the organic molecule react to form the product. So the base forms an important role. So this reaction, the reaction that gives this as the product, is an E2, or more than likely an E2 mechanism. The reaction that gives this as the product more than likely is an E1 mechanism, because there's not a strong base to react with the alkyl halide in that most important step. So bottom line is, if you're asked to do a synthesis, you will more than likely not use an E1 mechanism. Number one, because the percentage yield is typically lower compared to the E2 mechanism. And number two, as you'll see later on, there are a lot of side products because of the formation of the carbocation intermediate. But we'll say more when we conclude in a synthesis problem. Let us turn our attention now to another reaction. This is the dehydration reaction. So let's look at this molecule here. It's methyl cyclohexanol. It's an OH. In the presence of an acid, note carefully an acid. Water here is a solvent, and heat indicates that more than likely we would like to get an elimination reaction. But let's look at the products. We have two products that are observed, 1 and 2. And we will observe that this is the major organic product and this is the minor organic product. Another observation you should make is that the OH is a very poor leaving group. Notice it's not the bromide anymore. The OH is a poor leaving group. Why is it a poor leaving group? Because OH negative is a conjugate base, and that is a strong base. Of course, as you know, KOH is a strong base. So OH is a poor leaving group. In the presence of an acid, it becomes a good leaving group, as we'll see in the next slide. So that's why this reaction is called an acid catalyzed unimolecular E1 elimination or dehydration. Let's look at the mechanism to see why we need all these reagents and to see how these products are formed. The first step of the mechanism, as you can imagine, acid catalyzed. Remember, an acid here is typically represented by H plus, a proton. Remember, one definition of an acid is it's a proton donor. So it will donate its proton to the base. Notice this is a base, Lewis base, electron pair donor. So it will protonate this O to give OH2. As you can see here, with these electrons going to the OH2 plus, that's water. So that becomes a very good leaving group. So OH2 plus is an extremely good leaving group. So this now becomes the rate determining step to form the carbocation right here, and that's a tertiary carbocation. That's a tertiary carbocation we have here. Let's look at the next slide to see what happens with that tertiary carbocation. The slide looks a bit crowded, but let's walk you through it. Here is the carbocation, the tertiary carbocation. Positive charge is right here. On the adjacent carbons, here's a hydrogen, A. On the other adjacent carbon, another hydrogen, which we'll call C. On the third adjacent carbon is another hydrogen, which we'll call B. So it's possible to form a double bond here. It's possible to form a double bond here. And we've seen it here. It's possible to form a double bond here. And here it is. What you'll quickly recognize is that this alkene is the same as that alkene. So it's the same product. So in practice, we have just two products, 1 and 2. You can predict the major product would be this is the major product. Why? Because it is the most substituted alkene compared to this one, which is disubstituted, and this here is in fact trisubstituted. So again, if you're doing an E1 reaction, you should be able to predict the major product, and you should be able to write a mechanism which is a step-by-step description of the reaction using arrows to indicate electron movement. Let us look at another molecule. This is a slightly different molecule here from the one we looked at previously. You'll notice here that now we have 1, 2, and 3 possible products, 3 different products. So now you see why you cannot use an E1 mechanism for synthesis. You have a bunch of side products. So we can work this one through. I won't give you the mechanism for this, but we can work it through to show you why we have 3 possible products. It's acid catalyzed, so this OH becomes a good leaving group in the presence of an acid. We form the carbocation right here. So as you can imagine, we can form a double bond here, and here it is. We can form a double bond here, and here it is. Or we can form a double bond here, and here it is. Of course, forming a double bond, and forming a double bond here, and here it is. So we have 3 possible products here when we carry out an E1 dehydration on a molecule like this. Let us look at another observation that we can use the mechanism to explain what's happening here. So let's look at this molecule here. It's an alcohol. Here's the OH. And here's an acid in the presence of heat. And here's water as our solvent. If it's an E1 elimination, as you'd expect, because it has a proton and we have a good leaving group, that can be converted by converting OH into OH2+. You would expect the carbocation here, and you would expect the double bond to form right here. And here it is. So that's why this is called the expected product. Notice there are no hydrogens here, because that's a methyl, a methyl, a methyl. So you will not form a double bond here, because there are no hydrogens on the adjacent carbon of the carbocation. So you'd form this as the expected product. But this is an unexpected product that is observed when this reaction is carried out. So let us see if we can use the mechanism to explain the formation of this unexpected product. Notice it's different from the expected product. So let's look at the mechanism to see what's happening. Okay, so we'd expect in the first step the OH being a base, the acid here being the catalyst, converts the OH into a good leaving group. These electrons bond or goes into the oxygen to form water as a good leaving group, leaving behind a carbocation right here. Water acts as a base in this case, a weak base, but acts as a base, pulls off this hydrogen, these electrons swing in to form our expected product. Again, I want to emphasize, you'll be asked to write mechanisms, because we want to make sure you understand how reactions work, because you will see products that are unexpected and you will be asked to explain. And of course, for us as organic chemists, when you're asked to explain a product, the formation of a product, we're asking you to use arrows to indicate electron movement and give a step-by-step description of the reaction. So this is a step-by-step description to show the formation of the expected product. The unexpected product, however, involves the same carbocation here. So it's written again down here. Secondary carbocation. You will recall the stability of carbocations is the tertiary is more stable than the secondary and more stable than the primary. Since this is a secondary carbocation, it can be transformed into a tertiary carbocation by the migration of this methyl group with its electrons. Notice I'm circling the entire group with the electrons, the bonding electrons. That's called a methide anion. So if this entire group moves, methyl group moves, as indicated by that arrow, what's left behind is a carbocation, which is now a tertiary carbocation. So this methyl group has moved, and here it is. And what's left behind is a tertiary carbocation. As expected, water, being a base, can abstract this hydrogen as a proton. These electrons can swing in to form the double bond, and this is the unexpected product. So if you're asked to write a mechanism to explain the formation of this unexpected product from this as a reactant, this would be it. Using arrows to indicate electron movement and giving steps, step number 1, step number 2, step number 3, step number 4, a step-by-step description of the reaction. Okay? And let us look at a slightly different reactant. In this case, it's a 1,2-diol. Notice 1,2. So it has an OH and an OH on adjacent carbons. Let us see if we can apply the concepts and knowledge that we have just learned to predict the product that's formed if we should put the 1,2-diol in an acid and a water as a solvent and heat. As you expect, water is a base, so you'd expect this to react with the proton, converting it to a good leaving group, and something happens. So let's look at the next slide to see what happens. Okay, so as expected, we can get a protonation of the OH from the proton, the acid that's added as a catalyst, to form OH2, which of course, as we know, is a good leaving group, and it takes these electrons as indicated by that arrow to form water, and what's left behind at this carbon here is a carbocation. As you can imagine, carbocations are not very stable. This one happens to be a secondary carbocation. Let's see if it can rearrange to produce a more stable carbocation. Here's one way it can rearrange. This entire methyl ethyl group here, we call it an alkyl group since it's two carbons, more than one. This entire alkyl group can migrate to this carbon. Hence that arrow is showing this entire alkyl group is migrating over here, and here is that alkyl group with its electrons. We call that a 1,2 alkyl shift. So what's left behind is a carbocation right here. This carbocation is very stable because, as you can see, these electrons can participate in resonance to give us a resonance stabilized intermediate. This resonance structure here, if this hydrogen is removed as a proton and these electrons swing in, we have the aldehyde. So this mechanism explains the reaction of going from reactant here in the presence of an acid to form an aldehyde as the product. This has a name, and it's called the Pinacol Rearrangement. That's the Pinacol Rearrangement, which is the rearrangement of a 1,2. Make sure it's a 1,2 diol in the presence of an acid. So look out for that. Let's see if we can now apply all that we have learned into synthesis. So this is the application of elimination reactions. You'll see this question as a question on your quiz and on your exam because it gives a good test of your understanding of the material, because you now have to apply that information to solving problems. So let's see, show how to carry out this transformation. So here's your starting material, and here is the product. And this is done typically in industry, especially in the pharmaceutical industry. We have a starting compound and we have a target molecule that we're trying to make. And so you have to put all the chemistry, all the type reactions that we've studied to see how we can show how to carry out that transformation. First, as chemists, especially as organic chemists, and scientists, we have to carry out the observation, and we have to do a retrosynthesis. How do we put all this together to come up with the target molecule? So let's start over here with the target molecule. We notice here there is a carbonyl, a ketone functionality. And so the next question we ask ourselves is, how do we make a ketone? What type reaction can be used to make a ketone? And the answer is, we can make a ketone from a secondary alcohol by oxidation. So if you remember the type reactions that we have done, it's just a matter of applying the type reactions here. So if we can get an alcohol here, we just have to oxidize it. Looking at the reactant, we see a good leaving group. Good leaving group indicate to us that in the presence of base and heat, we can do an elimination reaction, dehydrohalogenation reaction, to get an alkene. If we have an alkene, we can convert that to an alcohol using an addition reaction or hydration, in this case an antimacognicoff hydration. Let us look at another way of carrying out a similar analysis. So, if you had, starting with our target molecule here, functional group here is a ketone. How do we make a ketone? We make a ketone by oxidation of an alcohol. And this would have to be the alcohol that's oxidized to get this. If we had this alcohol, what molecule do we need to make this alcohol? We need an alkene to make this alcohol. By hydration, in this case, remember there are two types of addition. One is the Markovnikov addition, and the other one is the anti-Markovnikov addition. In this case, you need to add your OH here, which would be the anti-Markovnikov addition. So if you had this alkene, you can make that alcohol. How do you make this alkene? If you had this alkyl bromide, you can do an elimination reaction to make that alkene. So that's another strategy. As you can see here, you will not readily know the answers for synthesis. It's a problem, a question that you'll have to solve by applying all of the chemistry and reaction types and knowledge that we have covered. So let us put all of this together and see if we can put reagents for these different types of reactions here. And that's shown in the next slide. So if we had an alkyl bromide, we know in the presence of heat and alcohol, we can do an elimination reaction, E2, to form an alkene. If we had an alkene and we need a secondary alcohol, adding the alcohol here, it's an anti-Markovnikov addition, hydration, and here are the reagents. Borane in the first step, notice it's a two-step reaction, and hydrogen peroxide in the presence of base to give this alcohol. If you have this alcohol here, it's just a matter of an oxidation. So now you have to pick a good oxidizing agent. One, of course, that comes to mind is potassium permanganate in the presence of base to give our target molecule. So that's what's expected. If you're asked, show how to carry out this transformation, what's expected is right here. The steps showing the reagents. Notice this is a different type question from your mechanism. We're not showing the steps in terms of how a particular reaction occurs, but here we're using different types of reactions to transform a reactant starting material into a different target molecule. I think this is the end of the chapter. So this is the last lecture for chapter 12, elimination reaction. So please go ahead and review the material for elimination reaction. We won't have a quiz this coming Thursday, which is the 21st, but plan on a quiz on the following Thursday, which would be the 28th, and this would be over elimination reactions. Okay, so continue to study hard, and if you have any questions, you can tune into the virtual office hours, and I'll get those questions answered for you. Okay, so continue to study hard, and I'll post the next lecture probably in a week or so. Okay, bye.